In the name of Allah, the most gracious, the most merciful, I am Engineer Hani Kamil. In this video I am going to talk about medium voltage overhead line, especially if there is a conductor or open conductor or like first ground fault with high impedance, and how the protection can sense and clear this fault. So first of all, we need to know our system. So let's see it. Now I have 66 kV bus, then circuit breaker for HV side of our transformer, then current and voltage measurement CD and VT, then our transformer TR1 25 MVA 66 over 11.8 kV and DYN 11, and neutral point is solid ground. Then circuit breaker for 11 kV side, and then CT and VT for current and voltage measurement. Then there is 11 kV bus taken from transformer to 6 feeders, as we can see. Each feeder is 12 kilometer, and at each kilometer there is one distribution transformer. It's from 11 kV to 0.4 kV of 400 volt, feeding distribution loads. This transformer is 200 kilovolt ampere, 11 kV to 400 volt. It's DYN 11. And our loads, here I can make unbalanced loads because it's normal for distribution loads. Same for all the 6 feeders. Then our feeder for feeder number 1, same other feeders, but I bought interrupter or circuit breaker only for red phase to cut this phase, to make phase loss. As we can see, fault 1 to cut 100% from line, fault 2 to cut 75%, fault 3 to cut 50%, fault 4 to cut 25%, and fault 5 to remove only one phase from last load. So this will simulate conductor loss or phase loss. Our measurement here: transformer 166 kV side, voltage, magnitude and angle, current magnitude and its angle, megawatt, megavar and power factor. For current, we'll make analysis positive and negative and zero sequence values. Then transformer number 1 11 kV side, we'll do same: voltage, magnitude and angle, current magnitude and angle, megawatt, megavar, power factor, positive and negative and zero sequence for current. And then feeder number 1 11 kV, voltage, magnitude and angle, current magnitude and angle, megawatt, megavar, power factor, and for current also same. Now this from these 6 switches we can make control for opening the lines, partitions. This feeder number 1 protection is over current and earth fault relay. As you can see, this over current function, earth fault function, negative sequence over current function. and this is a setting. Negative sequence now disabled. First to make the study and then we'll enable it. Lookout relay. Now we'll make run for our model. We can see the measurements. System is stable, but we can see there is some current unbalance because the load is unbalanced. This feeder number 1 11 kV side, the load unbalance, few unbalance available, and load 2 megawatt 1 megavar. And we can see the positive sequence value, negative sequence value, and zero sequence. Negative sequence value is available because the load is unbalanced. Zero sequence is not available because our HV side for distribution transformer is delta side. This transformer number 1 11 kV side. This is the measurements. Of course, it is the total of 6 feeders, and this 66 kV side for our transformer. Before we make fault, this is the value for positive and negative and zero sequence for feeder number 1. Now we'll make fault 5. This will remove last load, only one phase from last load. We can see the imbalance increased and phase A or phase R already less current, and zero sequence value increased. Again, after removing the fault, value come same before, and after putting the fault again, we can see or we can notice the increasing of negative sequence value. Fault number 4, remove 25% from line, so negative sequence increased because more imbalance. There is some zero sequence value because of a charging current of the 3-phase or for the line. Before it was 0 because the 3-phase was available. Now we cut one phase. Fault number 3, zero sequence increased for the feeder. And for all the system. Fault number 2, removing 75%, increasing negative sequence value. Fault number 1, removing one phase for all the line. So negative sequence current increased. So we can note now that with imbalance or phase loss, negative sequence increased, because our HV side for distribution transformer is delta, so negative sequence will increase, but zero sequence will not increase because our delta side is there is no not allowing zero sequence current. So we can see now this during loading condition, and system only on load because unbalanced load. This is a 5 ampere in negative sequence current, and for removing only last load it come 8 ampere for negative sequence current. So minimum setting now we can put less than 8 ampere. And of course we need to distribute the loads to minimize the negative sequence during normal operation. So now I will enable the negative sequence value. This is my setting. It's 0.05 ampere in secondary circuit. So in primary circuit for current transformer 7.5 ampere. So it's less than the 8 ampere, so the system can trip or even lose one load. So let's see it. We'll make run. Now this is in normal condition, system is stable and no trip. Now we'll enable fault number 5, removing only one phase from last load. Current is more than the setting, so and after time delay the system trip. You can see only feeder 1 only trip, transformer board transformer didn't trip. We'll make reset for the relay because we already removed the fault. Now we'll do feeder 4 25%, negative sequence increased, and it should also trip. That's what happened. Now I'll clear the fault and I will make reset. I will do fault 3, 50% from line removed, one phase, and same trip happen. Same will happen also for fault 2 and fault 1, but let's see our measurements or records for distribution record, disturbance recorder. We have phase overcurrent trip and earth fault trip and negative sequence overcurrent trip. We'll see which signal is trip the system. This is our records. This is when system started, some inrush current for charging current, then system become almost a 3-phase same. Here when we removed one load, one phase, R phase, so negative sequence already make trip, earth fault didn't make trip, overcurrent, phase overcurrent didn't make trip. Next, when we remove 25% from line, only red phase drop. Some earth fault, some neutral residual current is available. This charging current for lines, same negative sequence over current trip only. And here when we removed 50% from line, one phase, red phase, so current in red phase drop, no overcurrent, phase overcurrent, no phase overcurrent, no earth fault, only negative sequence over current trip. So now our conclusion, unbalance already increasing the negative sequence value, so we need to distribute the loads over the system, so we can put the right setting for negative sequence over current to be more sensitive, so it can isolate the feeder if there is one conductor loss or one phase loss. Thank you for watching this video, and I hope this video answer for your clarification, especially the engineer who asked about this point. This is my contact as shown, and see you in next video.